When starting a large horsepower motor with a soft starter, a temporary imbalance in the line currents can occur, and this creates a harmonic load on the neutral conductor. This happens because soft starters typically use thyristors or other electronic devices to gradually increase the voltage applied to the motor. This gradual increase results in a non-sinusoidal current waveform. The magnitude of the harmonic load on the neutral depends on several factors. These factors include firstly, the motor size and type, secondly, the soft starter settings, and thirdly, the system impedance. For a 300 horsepower 480 volts motor, the harmonic load on the neutral during starting can be as high as 10 to 20% of the motor's rated current. This means that for a 300 horsepower motor, the neutral current could reach approximately 60 to 120 amps. In general, a neutral conductor is required for loads that create an imbalance in the line currents. This includes firstly, single-phase loads, for example, lights and receptacles, and secondly, three-phase loads with nonlinear characteristics such as adjustable speed drives and soft starters. For a 300 horsepower pump motor with a soft starter, it is strongly recommended to provide a neutral conductor in the service. This will ensure that any harmonic currents created during starting are properly accommodated and will prevent potential overheating or damage to the electrical system. There are a few additional considerations. Firstly, the neutral conductor should be sized to carry the harmonic load, which can be determined through calculations or consultation with a qualified electrician. Secondly, the neutral conductor should be bonded to the system ground to ensure proper operation of the soft starter and to protect against electrical hazards. Thirdly, it is important to consult the manufacturer's instructions for the specific soft starter being used for any specific requirements or recommendations regarding neutral service. When installing a soft starter, it's crucial to understand the role of the neutral conductor, especially with large motors. Soft starters don't just switch a motor on, they gradually increase the voltage to reduce stress on the motor and the electrical system. This gradual increase, however, introduces harmonics, which can affect the neutral conductor. Harmonics are additional frequencies in the electrical current that aren't part of the standard 60 Hz signal. These harmonics can cause the current in the neutral wire to increase, potentially leading to overheating and other issues. The size of the motor, specifically a 300 horsepower motor in this case, is a significant factor. Larger motors draw more current, and therefore the potential for harmonic generation is greater. The soft starter settings also play a role. The way the soft starter is configured to ramp up the voltage can influence the amount of harmonics produced. System impedance, which is the opposition to the flow of alternating current in the electrical circuit, can also affect the harmonic load on the neutral. Higher impedance can limit the flow of harmonic currents, while lower impedance can allow them to flow more freely. A neutral conductor is generally required when there are loads that create an imbalance in the line currents. Single-phase loads, such as lights and receptacles, draw current unevenly across the phases, requiring a neutral to carry the unbalanced current back to the source. Three-phase loads with nonlinear characteristics, like adjustable speed drives and soft starters, also generate harmonics, which contribute to neutral current. For a 300 horsepower motor using a soft starter, providing a neutral conductor is strongly recommended. Without a neutral, the harmonic currents can circulate through other grounding paths, potentially causing problems with other equipment or creating safety hazards. The neutral conductor needs to be sized appropriately to handle the expected harmonic load. The specific size will depend on the motor's rated current and the percentage of harmonics generated by the soft starter. Consulting with a qualified electrician or engineer is crucial to determine the correct size. The neutral conductor must be properly bonded to the system ground. This bonding ensures that the neutral is at the same potential as ground, which is essential for safety and proper operation of the soft starter. Improper grounding can lead to voltage differences between the neutral and ground, increasing the risk of electrical shock. Always refer to the soft starter manufacturer's instructions. The manufacturer may have specific requirements or recommendations for neutral service based on the design of the soft starter. These instructions should be followed carefully to ensure safe and reliable operation. In summary, when using a soft starter with a 300 horsepower motor, a neutral conductor is typically required. The neutral should be sized to handle the harmonic load, properly bonded to ground, and installed according to the manufacturer's instructions. Understanding the role of the neutral and taking these precautions will help prevent electrical problems and ensure the safe operation of the motor and the electrical system. Let's delve further into the nuances of neutral conductors in soft starter applications, particularly focusing on the harmonica aspects and practical considerations. The presence of harmonics isn't just a theoretical concern, it has tangible implications for the electrical system's performance and safety. Harmonics distort the sinusoidal waveform of the alternating current, leading to increased heating in conductors, transformers, and other equipment. This increased heating can reduce the lifespan of these components and potentially cause failures. In the context of a soft starter, the thyristors or other semiconductor devices used to control the motor's voltage are the primary source of harmonics. These devices switch on and off rapidly, creating non-sinusoidal current waveforms. The specific harmonics generated depend on the firing angle and control strategy of the soft starter. Common harmonics include the third, fifth, and seventh, although higher order harmonics can also be present. The neutral conductor provides a path for these harmonic currents to return to the source. Without a neutral, the harmonic currents would circulate through other paths, such as the grounding system, which can lead to problems. Grounding systems are designed to provide a low impedance path for fault currents, not for continuous harmonic currents. When harmonic currents flow through the grounding system, they can cause voltage drops, which can interfere with the operation of sensitive electronic equipment. Furthermore, harmonic currents can increase the risk of electrical shock if the grounding system is not properly designed. Sizing the neutral conductor correctly is critical. The National Electrical Code, or NEC, provides guidelines for sizing neutral conductors based on the expected load. However, in applications with significant harmonic content, the standard sizing methods may not be adequate. The NEC Article 10c addresses neutral conductors. The neutral conductor may need to be oversized to handle the additional harmonic current. To determine the appropriate size, a harmonic analysis should be performed. This analysis involves measuring or estimating the harmonic currents present in the system and then calculating the required neutral conductor size. Several factors influence the harmonic content, including firstly, the type of soft starter, secondly, the motor load, and thirdly, the system impedance. Some soft starters have built-in harmonic mitigation features such as filters or reactors, which can reduce the amount of harmonics generated. The motor load also affects the harmonic content. Motors operating at light loads tend to generate more harmonics than motors operating at full load. System impedance plays a crucial role in determining the flow of harmonic currents. Low impedance systems allow harmonic currents to flow more freely, while high impedance systems tend to limit their flow. The location of the soft starter within the electrical system can also affect the harmonic content. Soft starters located closer to the source of power tend to have a greater impact on the overall system harmonic levels. Grounding is another important consideration. The neutral conductor should be bonded to the grounding system at the service entrance. This bonding ensures that the neutral is at the same potential as ground, which is essential for safety and proper operation of the soft starter. The grounding system should be designed to provide a low impedance path for fault currents and harmonic currents. In some cases, a separate equipment grounding conductor may be required to provide an additional path for fault currents. The equipment grounding conductor should be sized according to the NEC and should be connected to the soft starter enclosure. Proper installation of the neutral and grounding conductors is essential. All connections should be tight and secure to minimize resistance. The conductors should be routed in a way that minimizes the risk of damage. The conductors should be protected from mechanical damage and exposure to corrosive substances. Regular maintenance of the soft starter and the electrical system is also important. The soft starter should be inspected periodically for signs of wear or damage. The connections should be checked to ensure that they are tight and secure. The grounding system should be tested to verify that it is functioning properly. Any problem should be corrected promptly to prevent further damage or safety hazards. In addition to the technical aspects, it's also important to consider the regulatory requirements. The installation of electrical equipment must comply with the NEC and any applicable local codes. These codes provide specific requirements for the installation of neutral conductors, grounding systems, and other electrical components. It's important to consult with a qualified electrician or engineer to ensure that the installation meets all applicable codes. Furthermore, it's important to document the installation. A detailed record of the installation, including the size of the neutral conductor, the grounding system configuration, and any other relevant information should be maintained. This documentation can be helpful for troubleshooting problems in the future. In summary, the neutral conductor plays a critical role in soft starter applications, particularly with large motors. The neutral provides a path for harmonic currents to return to the source, preventing them from circulating through other parts of the electrical system. Sizing the neutral conductor correctly, ensuring proper grounding, and following all applicable codes are essential for safe and reliable operation. Consulting with a qualified electrician or engineer is highly recommended to ensure that the installation meets all requirements. Harmonics are a significant concern when using soft starters, particularly with motors as large as 300 horsepower. Harmonics are generated due to the nonlinear nature of the electronic components within the soft starter, primarily the silicon-controlled rectifiers or SCR, also known as thyristors. These SCR chop the sine wave of the alternating current voltage to gradually increase the voltage applied to the motor during startup. This chopping action creates voltage and current waveforms that are no longer pure sine waves, but rather contain harmonic frequencies that are multiples of the fundamental frequency, which is typically 60 Hz in North America. The most common harmonics generated by soft starters are the odd-numbered harmonics, such as the 3rd, 5th, 7th, 9th, and so on. These harmonics can have several detrimental effects on the electrical system, including increased heating of conductors and transformers, voltage distortion, and interference with sensitive electronic equipment. The neutral conductor plays a critical role in mitigating the effects of harmonics. In a three-phase electrical system, the neutral conductor is intended to carry any imbalanced current between the phases. When harmonics are present, they can cause a significant increase in the current flowing through the neutral conductor. This is because the triplet harmonics, which are the odd multiples of the third harmonics such as the 3rd, 9th, 15th, and so on, are additive in the neutral conductor. This means that the neutral current can be significantly higher than what would be expected based on the fundamental frequency current alone. For example, if a 300 horsepower motor has a full load current of approximately 360 amps at 480 volts, and the soft starter generates 20% total harmonic distortion, the neutral current could be as high as 72 amps due to the harmonics alone. Therefore, it is essential to size the neutral conductor appropriately to handle the additional harmonic current. The National Electrical Code, or NEC, provides guidelines for sizing neutral conductors, but these guidelines may not be sufficient in applications with significant harmonic content. In such cases, it is necessary to perform a harmonic analysis to determine the actual harmonic currents that will be present in the neutral conductor. The harmonic analysis can be performed using specialized software or by taking measurements with a harmonic analyzer. Once the harmonic currents are known, the neutral conductor can be sized accordingly. As a general rule of thumb, the neutral conductor should be sized at least 150% of the phase conductors in applications with significant harmonic content. In some cases, it may be necessary to size the neutral conductor equal to or even larger than the phase conductors. In addition to sizing the neutral conductor appropriately, it is also important to ensure that it is properly grounded. The neutral conductor should be grounded at the service entrance and at any separately derived systems. The grounding conductor should be sized according to the NEC and should be connected to a grounding electrode system that meets the requirements of the NEC. Proper grounding is essential for safety and for mitigating the effects of harmonics. A properly grounded neutral conductor provides a low impedance path for harmonic currents to flow back to the source, which helps to reduce voltage distortion and interference with sensitive electronic equipment. In addition to sizing and grounding the neutral conductor appropriately, there are several other steps that can be taken to mitigate the effects of harmonics. These include, firstly, using harmonic filters, secondly, using line reactors, and thirdly, using shielded cables. Harmonic filters are designed to block specific harmonic frequencies from flowing through the electrical system. They are typically installed at the source of the harmonics, such as at the soft starter. Line reactors are inductors that are installed in series with the power lines. They help to reduce the harmonic current by increasing the impedance of the circuit at the harmonic frequencies. Shielded cables can help to reduce the amount of electromagnetic interference caused by harmonics. The shield is grounded and provides a path for the harmonic currents to flow back to the source, which reduces the amount of radiation emitted by the cable. In summary, harmonics are a significant concern when using soft starters with large motors. The neutral conductor plays a critical role in mitigating the effects of harmonics. It is essential to size the neutral conductor appropriately, ensure that it is properly grounded, and take other steps to reduce the harmonic content in the electrical system. Consulting with a qualified electrical engineer is highly recommended to ensure that the electrical system is designed and installed properly to handle the harmonics generated by the soft starter. Let's further examine the specific considerations for neutral sizing and grounding in soft starter applications, particularly focusing on the practical aspects and code requirements. When sizing the neutral conductor for a soft starter application, it's crucial to go beyond the basic NEC guidelines and consider the harmonic content generated by the soft starter. As mentioned earlier, the tripling harmonics, which are odd multiples of the third harmonic, are additive in the neutral conductor. Therefore, a neutral conductor must be sized to carry the increased current caused by these harmonics. To accurately determine the neutral conductor size, a harmonic analysis is recommended. This analysis can be performed using specialized software or by taking measurements with a harmonic analyzer. The analysis should take into account the following factors: firstly, the motor's full load current, secondly, the soft starter's total harmonic distortion percentage, and thirdly, the system's impedance. The motor's full load current is the current that the motor draws when operating at its rated horsepower and voltage. This information can be found on the motor's nameplate. The soft starter's total harmonic distortion percentage is a measure of the amount of harmonic content generated by the soft starter. This information can be obtained from the soft starter manufacturer. The system's impedance is the opposition to the flow of alternating current in the electrical system. This information can be obtained from the utility company or by performing an impedance study. Once these factors are known, the harmonic analysis can be performed to determine the neutral current. The neutral conductor should then be sized to carry at least 125% of the calculated neutral current, as per the NEC. In some cases, it may be necessary to size the neutral conductor even larger, depending on the specific application and the harmonic content. For example, if the harmonic analysis indicates that the neutral current is greater than 50% of the phase current, the neutral conductor should be sized equal to the phase conductors. In addition to sizing the neutral conductor appropriately, it is also essential to ensure that it is properly grounded. The NEC requires that the neutral conductor be grounded at the service entrance and at any separately derived systems. The grounding conductor should be sized according to the NEC table 102. C and should be connected to a grounding electrode system that meets the requirements of the NEC Article 250. The grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, ground plates, or metal underground water pipes. The grounding electrode should be installed in accordance with the NEC Article 250. In addition to grounding the neutral conductor at the service entrance and at any separately derived systems, it is also recommended to ground the neutral conductor at the soft starter itself. This can be achieved by connecting a grounding conductor from the soft starter's neutral terminal to the equipment grounding conductor. This provides an additional path for harmonic currents to flow back to the source, which helps to reduce voltage distortion and interference with sensitive electronic equipment. When installing the grounding conductor, it is important to ensure that it is properly sized and connected. The grounding conductor should be sized according to the NEC table 102. CN should be connected to the soft starter's neutral terminal and the equipment grounding conductor using approved connectors. The connection should be tight and secure to ensure low impedance path for fault currents and harmonic currents. In addition to grounding the neutral conductor and the soft starter, it is also important to ensure that the entire electrical system is properly grounded. This includes grounding all metal enclosures, conduit, and other non-current carrying metal parts. This helps to minimize the risk of electric shock and to provide a low impedance path for fault currents to flow back to the source. The equipment grounding conductor should be sized according to the NEC table 122 and should be connected to all metal enclosures, conduit, and other non-current carrying metal parts using approved connectors. The connection should be tight and secure to ensure a low impedance path for fault currents. In summary, sizing and grounding the neutral conductor are critical considerations in soft starter applications. The neutral conductor must be sized to carry the increased current caused by harmonics, and it must be properly grounded to provide a low impedance path for fault currents and harmonic currents. Consulting with a qualified electrical engineer is highly recommended to ensure that the electrical system is designed and installed properly to meet the requirements of the NEC and to provide safe and reliable operation.